Before we get into the content of the workshop, yes, my name is Luca. I'm one of the co-founder of Doensec. We're a security consulting boutique, and one of our specialization is around ElectronJS security, from which the training and the tool were born. Today's workshop is actually hands-on on electronegativity. So I thought instead of me teaching you the great things that Lorenzo and the team of maintainers are doing, I would rather give them the possibility to showcase that. I will be teaching the class in Vegas together with other instructors that will help me. And I wanted to contextualize exactly what we are seeing today in the context of the ElectronJS training. So let me share my screen and kind of show you a bit of what is the plan for the training and for today. So the training will cover everything you basically need to know around ElectronJS security. We'll start with the Electron overview and then talk about internals. So exactly we'll go very deep on how Electron works and to the point that we will be understanding the IPC and the deep internals of the framework. After that, and that's basically day one. After that, we will go into security model and what we call attacking the application iceberg. Electron is not a browser, and so a lot of the security mechanisms that are present in browser do not apply, or they apply in a different way in Electron. And as a result, I think it's pretty important to understand and contextualize the security model. And then we will go into a set of discussion around attacking and defending both the framework in terms of configuration and misconfiguration, as well as the application custom code. And then finally, in the last session, which is called Electronegativity and Security Automation, we'll explore some of the tooling and some of the techniques that can be used for security automation. And today, what we will see today from Lorenzo is basically an extract of that session. And we will cover what is electronegativity and even how to write custom checks. But before that, I think it's important to give a bit of context also on Electron. I assume that all of you are already familiar with Electron. If not, let me give you a 40 seconds introduction, and hopefully that's sufficient. If you know a bit of JavaScript and Node, you can probably follow the exercise with no problem. So Electron is really the combination of Chromium, Lib Chromium content, Node.js, and some native API that have been built on top of that. The idea is to build desktop application with web technologies. And so by combining those, foundation, it's possible to achieve that in a way that is fairly easy if you know how to build, web apps. In order to talk about misconfiguration and kind of understand what's the context for some of the vulnerability and misconfiguration that Lorenzo will showcase, it's important to understand how Electron apps are executed. These slides are extracted from the training. And of course, during the training, we'll be covering a lot more into, the details of this. But at a high level, when you're running an Electron app, you're running a format called, the file is generally called app.azar, that basically contains the entire application. It's an archive. It's not a compressed archive. It's just an archive with concatenated files that contains a set of important files, one of which, the package.json, is the file used by the framework to understand the manifest of the application. From the manifest, the application, Electron knows which is the main process and will bootstrap with Node a JavaScript file. And in the main process, generally you want to have some UI, and the way to get a renderer that is defined as a browser window, browser view, or web view tag, is generally to bootstrap such renderer from the main process using one of those primitives. And the renderers can be set up using a different set of configuration. And depending on which configuration you use, you might or might not create security vulnerability due to the misconfigurations. And so some of the checks that, again, Lorenzo will showcase are related on how web preferences, which are those settings, are set up when creating a renderer. There's obviously a lot more to say here, but again, this was just an overview to explain when we talk about misconfiguration, what we're really talking about is web preferences misconfiguration. And then finally, there is a lot to do in Electron app security. You could start thinking about what are the problems in the foundational components of the platform, the framework itself, so some misconfiguration and bugs in the framework, to the top, right, to your application and how your custom code has been built. There's a lot to do, and basically that was that is what started working on Electronegativity back in 2017. And with that, I will leave to Lorenzo to kick off the real workshop. Thanks, everyone.
Thanks, Luca, for the introduction. I'm going to share my screen quickly. All right. So, as anticipated, I'm Lorenzo Stella, and basically I'm a security engineer at Doyenstech, and I've been providing like the research work, part of the research work and part of the development work for Electronegativity, which is this SAST tool that was specifically built to analyze and identify vulnerabilities in Electron-based application. And because of this, it will be the cornerstone for this workshop. And yeah, so in the last year, we've been maintaining it, and it's been growing and evolving ever since. So this is currently the best tool on the market, and since it's open source, that allows you to achieve this automation. As anticipated by Luca, you may know from experience that performing security assessments on Electron applications can be really a daunting task if you don't know how to approach it, or what are the most common vulnerabilities to look for. And this is because we have to take note of the risks that are traditionally associated to the browser security model, or the ones associated to traditional web security, but also the common Node.js vulnerabilities, or other unique challenges and risks that are specific to the native APIs of Electron. So what Electronegativity does is running a batch of automatic tests that are inspired by the Electron security checklist that was initially put out by Luca back in 2017. And after that, it produces a clear report of any of the issues encountered, also reporting the severity and the confidence for each one. And obviously from 2017, its development has continued, and now features every check that covers a secure aspect of the framework usage. It's currently open source, and it's available both on GitHub and NPM. I invite you to test it out yourselves on a real-world application when you have the occasion after this training. Obviously, you can get back to me later if you have any questions, or you find any issue or any problems writing the checks. As I was saying, the code is open source right now with an open license, and it's maintained by the community, so it's not a commercial-grade solution. But some of you may already know this, but we are internally developing a much more precise and comprehensive SAST tool called ElectronJ that should help developers and security auditors to better and quicker identify bugs in these applications. So that's basically an improved professional version of Electronegativity. And with this, you'll get more checks that are run per scan, a better false positive or false negative rate, an inventory of the Windows secure setting, and an end-day scanner that relies on our private knowledge base, which is supported by our security researchers who constantly provide research on the framework. There are also some features related to internal scans, so you have the chance to track the security state of the application over time. And also, we created several reporting tools that produce a clear write-up of every issue encountered. So the target is to create a point-and-click tool for you ready to use. And hopefully we'll reach it by, I think, August. So now I'll drill down on some of these topics, starting from what a basic usage of Electronegativity looks like. Here you can see that the minimum argument required is the input one. using the -i command flag that specifies the directory of the target application. And we built Electronegativity to support the scans on whole project directories, single files, or other archives, which is a simple tar-like format that concatenates files into a single file. To spend a few words on it, Electron can read arbitrary files from these archives without unpacking the whole file. You will often find that the Electron applications that are packaged in your system are packaged using this particular format. And that is basically to solve some issues around the long path names on Windows, or also to speed up the require of all the files, and partially conceal the application source code from cursor inspection. As you can see here from this scan, you get a list of findings in a table, since it's a command line tool. And on the right, you can quickly consult on each of these links how the vulnerability works, what are the risks, the common exploitation methods, and other details that are useful for the auditor. So if you run it without options, it will by default run all the scans. And by doing Control-click on the link from the terminal natively, you should be able to open the URL in your browser. And here, for example, you can see that the custom argument JavaScript check has been found in the Electron application. And it is possible for the tester to check the online documentation and verify whether the vulnerability is actually present in the code of the application. What are the possible exclusions, if it's how to identify if it's a false positive or a false negative, and so on. And most of all, if you're an attacker, you will also have sometimes a detail on the exploitation, right? So it's not also the auditing, but this is also for red teaming or maybe bug hunters. We try to keep this wiki constantly updated. So yeah, it should be quite reliable. This is an overview of the command line options. And as we said, the most important is the -i1 for the input, but you may also need to pass other flags to improve the scan or filter the results. And like many other tools, it is also possible to use the severity and confidence flags to only return the findings over a certain severity or confidence threshold. And these two attributes change according to how the application is designed or on the presence or absence of a secure configuration. And we achieve this thanks to a second round of checks that I'll describe later, the so-called global checks. And the filtering attributes you can currently provide are for the severity, the usual high, medium, low, and informational, while for the confidence, you can set certain, fear, more tentative. And these are particularly useful for the automation since you can leverage these flags to easily integrate Electronegativity in your continuous integration pipeline. For example, by reading the exit status codes of Electronegativity and acting on that result. Or maybe if you don't want too much noise or you don't want the build to fail, you can specify the confidence to certain and maybe filter only the medium or high. One of the important things to consider with Electron is that the framework vulnerabilities can change significantly versions by versions. And this is due to secure defaults or maybe bug fixes or design changes. And so we had to tackle this aspect of the design in Electronegativity. And so we built the severity and confidence attributes of the findings to being altered depending on the version, or maybe we can also create new checks that check the configuration of the target application to determine if it's secure. So internally, you are able with Electronegativity to access a database of defaults across the various versions. And Electronegativity tries to infer the Electron versions the app is using in various ways and provide it to the check. Chances are that the tool will detect the installed version automatically, but if it doesn't, you may need to provide it with a dedicated command line flag using -e or -- Electron -version along with the version used. So in this example, we had to force with -e the version to 7 in order to get more accurate results. So keep in mind this if you're seeing where the results or things doesn't add up. If you're specifically looking for a class of vulnerabilities, you can specify single checks to be run with the -c or --" checks flag. And the option is case insensitive, and it allows you to provide all the check names in the checks directory below. Again, to give you an idea on how versatile a check can be, you may have noticed that in the displayed run, there's a check that is named the CSP global check. And the check is reporting that a CSP policy is set and it was determined to be weak. And we did this by integrating the official Google CSP evaluator library into the check so that you can already know if the application, first of all, has a CSP set and if that CSP is secure. These are some of the checks that are supported, but again, it's open source with an Apache 2.0 license, so we encourage you to contribute by adding the checks that you deem more useful, or that you use the most, maybe in your CI/CD. There is also an option to run Electron upgrade checks, and the intention of this feature is for developers to discover the breaking changes that will affect them when they upgrade to a newer version of Electron. As I was saying, the framework changes rather quickly, so the developers may want to understand if bumping of one or two major versions may break some features of the application. So there was this feature that was integrated actually by the Electron team itself in the tool. And to use this feature, we introduced a new argument, -u or --" upgrade. And when using this argument, the user passes along a string in the format of x.y, where x is the user's current version of Electron and y is the user's target version of Electron to upgrade to. For example, for an app that is currently using, say, Electron 4 and trying to upgrade to Electron 8, you would write 4.8. Just like many other assessment softwares, you can also configure Electronegativity to export the results of a scan. And the tool currently supports CSV and Serif output formats in order to facilitate the reporting process to the auditor. And yeah, you can use --" output for this. As a final note on the flags, you can use the -r or relative option to turn the absolute path into relative ones. By using these options, you won't be able to use the control key plus click option to open the file from the command line, but it's useful when exporting results for reporting. And also with the -v or --" verbose option, you can print a short description for every finding, which can be quite useful if you're not familiar with some of the check names or with some of the vulnerabilities which are reported. So you can quickly assess what is of interest for you. Talking about automation and CI/CD, one of the ways you can integrate electronegativity is to use the library programmatically. I anticipated this that you can use it as an NPM module globally, but you can also call it in a Node.js script. And you basically pass all the options as for the CLI. And when the scan ends, it will return an object that will contain the number of global and atomic checks that were run, any errors encountered while parsing the target project, and an array of the issues found, similar to this one. So you may be able to parse it and make decisions according to the results. If you use GitHub Actions, we recently had one of our first contributor on the project that joined the GitHub security team, and he integrated the tool as a GitHub Action that you can now find on the GitHub Action store. You can see here that all you need to do is using the action that is in the store, and then you can reuse the CodeQL action to upload the Serif result to your repository code scanning alert, so that you can track the issues right away on GitHub, and obviously try to secure your app. It's absolutely possible to integrate and run it in other popular CI/CDs too, and this is because you can run it basically as a dummy binary linter, installing it through npm, or by creating a dedicated Docker image if you're using it with your own custom checks in it, and you don't want to use the npm one. But yeah, for any issue, just ping me. It should be quite easy. If you use it every day, though, as an additional tool, you might want to mark the false positive issues returned by the tool. And because of this, we implemented a simple exclusion system that mocks the existing ESLint annotation syntax. I don't know if you're familiar with this, but basically all you need to do is inserting these eng minus disable inline comments, mentioning a specific check, and this will instruct the tool to ignore that line of code. This works both for JavaScript and HTML, obviously. It is also possible to provide multiple check names using both their snake case IDs or their construct names in line. And if you put an eng disable directive before any code at the top of a JavaScript or HTML file, that will disable the past checks for the entire file. For the moment, we don't support having a directive at the beginning of a function, like ESLint, to exclude the whole function, but we're working on it. For some global checks, obviously you can't disable them using this system. So there's always the -x command line flag, which can be used to exclude a list of checks. So that's a quick solution if you're not able to, or you don't like maybe inline comments. And now let's dive into contributing and writing your own checks. So as a requirement for this workshop, you were asked to read possibly the contributing section and clone the repository on GitHub. But if you didn't have the chance to do it earlier, I invite you to take a moment to clone it. And after the clone, you should first run an npm install and then launch the build script with npm run build. After that, you should be good to go. The entry point is in dist/index.js. I'm going to wait a couple of minutes. I'm going to do it with you so that everyone gets the time needed to do this. And then we'll carry on. If you encounter any issue while doing this, just ask. I'll be glad to help. Okay, let's try to maybe stop the share. And I can share the console. Okay. So as I said, let's retrieve the source from GitHub. Okay, then we cd init and then run npm install. Let's wait for the packages to resolve. Yeah, as I was saying, you will need after this step to transpile the code because we're using Babel to port some features, some recent ECMA script features. So after this, we'll need to run npm run build. Let's wait for a fast event. Okay, then I was saying npm run build, and this will allow us to transpile everything. Okay, then if you browse the project directory, you will see that you will have a source folder, and that is where the actual source code is located, and then a dist folder that contains, oops, my bad, that contains the actual transpiled code. Okay, let's carry on with the slides, and then I'm gonna spend a couple of words giving you an overview of how we built it. So there are 3 different check types that you can define in Electronegativity, and every check types use a different set of parsers for every file type. For JavaScript, the tool uses a combination of Esprima, Babel, TypeScript S3. For HTML, we use Serial to parse the DOM. And for JSON, for example, for parsing the package JSON files, we use the native JSON parse. And as you can see here, there are 2 different kinds of checks. There are non-atomic checks, which are executed after the first round of standard atomic checks. And they work on the array of issues which are generated by the first batch of checks to determine more vulnerabilities or maybe to discard false positives. So using this class of checks provides you with an improved decisional process, which comes in handy for checks that need to scan every JavaScript or HTML of the target application before determining the presence or the absence of a vulnerability. As I was saying, this is critical since many times you need to scan to inspect, for example, for CSP, you need obviously to look in every JavaScript or HTML file before determining if a CSP policy is set for the application or not. And with this, I was giving you the example of CSP earlier. You would use a global check, right? If you want your global check to have some property passed by the atomic checks, it's possible to do it. It's possible for atomic checks to share an additional property object when added to the initial issues array that is later used by the global checks to perform decisions. It's important to mention that the tool's design for the check has a very reasonable learning curve and allows you to write your own check rules easily and specifying only the checks you are interested in, also by using some dedicated command line flags I showed you earlier. Obviously, a check can be tuned to have very specific detection requirements. For example, while there's already a check for dangerous methods in electronegativity, if you, in your organizations, if in your development team, internally know that there's a certain internal function name or class that is insecure or that is often called insecurely, you can easily write a check to detect this inside the electronegativity. And because of this, I'll briefly introduce you to how the checks are designed and which steps you would need to take in order to write your own custom check. For anyone not familiar with AST, these are syntax tree representations of the abstract syntactic structure of the source code. And this is basically how electronegativity see the code that is scanning. In AST trees, each node of the tree denotes a construct that occurs in the source code. And what electronegativity does is navigating all the nodes from the top to the bottom and left to right. And for every node, its checks evaluate if the node is of interest or not, based on what came before or by just by what's the content of the current node. So what will happen here is that for every AST node, the tool will ask for every check if the node is of interest. And then the checks determines if a finding should be issued for its own. And that's exactly what we'll do. Since it's hard to visualize complex AST, rather than trying to figure them out ourselves, we can use several visualization tools to help us. One of these, and I think it's the most popular one, is astexplorer.net. It's a free service that allows you to input JavaScript on the right and then explore the representation of the AST on the left. And you can use the tool to understand and experiment with code as you begin writing your checks. So here on the right, you have your snippet. We see that it's an assignment. It's an assignment that requires the Electron package, and we only pick the shell object. And then we have a call expression. A call expression that have an argument that here is not expanded, but should be a fixed string. Now, for the sake of giving you an example, I'm going to pretend to write the code to detect the presence of an example function called OpenPath, which is actually dangerous in Electron since it could allow for arbitrary launches of executables on the user's machine. So we may want to detect this and maybe issue a finding. For now, the check will only report its use for additional manual inspection. But if we wanted, we could develop it to make it smarter and maybe only issue a finding if it finds that its parameter is user controlled, or discard it if it's a fixed string set by developers. This is an atomic check because it's not relying on the results of any other check to issue a finding. And because of this, it will be located on the atomic checks folder. You need to remember that for every check that you're writing, you will also need to specify the checks constructor carrying its own unique ID, a description, and that will be shown when users use -v, for example, a type, and the documentation reference URL. You might also want to import the source types and the attributes classes, which have the enumeration of the severity and confidence levels. In this case, it's a JavaScript check, so we set the source type to JavaScript, but we could also write check using an HTML or a JSON parser, for example. Now, the most important function here for every check is the match, which, as I was saying earlier, is called when the tool navigates to a new AST node. So every time that the tool navigates to a new AST node, you will have the match function that will be called passing the AST node. It also provides you with an AST helper object that contains some utility function that are related to some variable scope resolution and others, but we don't need it for the moment. To spend a couple of words on it, basically we are relying on ESScope, which is a library that tries statically to determine the content of some variables, for example, if they are coded. So it's quite useful, even if it's a static analysis tool, to try to infer if that variable is statically set at compile time, or maybe it's something that we cannot predict. We are looking for a function call, as I was saying. So we check that the current node type is a call expression, as we said earlier on our AST visualizer. And if it's not of interest, we'll instead return null. So every time you return null on a check, the tool will try to pass to the next AST node. We're then checking if the callee property is present and also matches our desired function name. Otherwise, it's some other call expression we don't care about, so we should carry on. As I was saying at the beginning, we can make this check a bit smarter by checking if it's a constant declared inline, so that we don't bother to issue a finding if that's the case. And that will help us obviously reduce the false positive. Finally, we can return a finding object if we are sure, and we can report the line, the column, and other metadata that are present in the checks constructor. We can refer to it when issuing a finding. Obviously, you can here play with it and tune the severity, the confidence, and the manual review flag according to your preference or to what you've seen before. As a final step, you should write the test cases, if possible, and remember to add the check in the index.js file present in the atomics check folder. And this is done to register your new check. Please remember this, otherwise when someone runs the scan with the no option, they won't have this check included. And then you're done. So you should always remember after writing your check to install any dependency you used, and then use npm run build to transpile the code with Babel. If you like, you can test your new check, only your new check, by pointing the tool to a test file with -i, and by using the -l option to only run the new check. Aside from call expressions, another common use case when writing checks is when we want to detect when a specific assignment construct is present in the code. I don't know how many of you are familiar with this flag, but it's usually used by developers to disable Node from rejecting self-signed certificates by allowing any unauthorized certificates. This is obviously a bad practice, and we want to discourage it. So we can now maybe try and have a go at writing a new check. And yeah, maybe if anyone, I'll try to give my solution, which will be a naive solution. But yeah, if anyone wants to send me their solution, I'm glad to look at them together. As I was saying, this is not a call expression, as we said earlier. So we are now looking at a new construct, which is an assignment. Let's start by exploring the AST together. We are using, again, the AST Explorer application to see that we should look for an assignment expression this time. And we should check both the left and right parts of the expression to actually check that the property is set to 0. So to recap, I listed here the steps I already showed you earlier. So we'll begin by creating a new check file in the source directory, finder checks, atomic checks, and adding it to the index.js of the same folder. We can then write our check for the unsafe setting using the example check for open item from the slides that we built together earlier. And once you're done, you can test again the check by using the -l flag. So let's try to do it. Okay. Okay, here we are again. Wait, I should search Sublime. Desktop 1. Okay, you should be able to see my screen. As I was saying, let's try to go to source finder checks, atomic checks, and here we create a new file. Okay. Let's switch to here. Okay, so as I was saying, we'll start by importing these source types, because we know that this will be a JavaScript check. So we'll need to be able to provide the basic structure for this kind of check. Okay, then we'll probably need to import the severity and confidence definition from the library that will allow us to follow the standard that is used throughout the tool. And then we're going to define the class. As I was saying, it's a node TLS reject unauthorized JavaScript check. We are keeping the camel case for the check names, for the class name of the checks throughout the code base. But there's no, I mean, you can do what you like if you're developing in-house these kind of checks. So in the constructor, we are gonna define our own options, but that's not of interest for now, because we'd like to go straight to the point and start defining our match function. Okay. So first of all, we can check the type of the node. We can check if the type of the node is maybe an assignment expression. And if it's not, we can, as I was saying, return null. And this will allow us to carry on with the auditing. Then, as I was saying, we need to look at the left property if it's there. And that's one thing that I advise you when you're writing these kind of checks. You may also want to make them as much robust as you can, because sometimes people will provide maybe strange code, or maybe code that doesn't even compile, that will be parsed anyway by the EST3. So as an extra safety, in order for your tool not to fail, even with strange or maybe malformed code, you may want to ensure that actually you will have a left and a right property, even in assignment. I know that's that sounds obvious, but it's not. Okay, so I was saying we look for the left, and then we look at the property name, and then maybe we look at left property name equals our infamous string, which is not-ls reject unauthorized. Okay, as I was saying, we check that. Wait, let me, maybe if someone can see better then. st node dot right dot value equals 0. Okay, what happens if we are in this situation? We are most probably looking at our assignment, so we must return the check result, which we call a finding. We provide the line. We provide then the column. This is only the start. You can also have the end. If you're trying maybe to highlight some code, you may want to pass the start and the end of the culprit. Okay, then you specify the ID. Then a description, which you may want to specify in the constructor, as I was saying. Maybe if you have an internal wiki, you can also specify a URL for the issue. Then we try to set the severity. So this is a very basic check. So we'll try to keep it as simple as possible. But here you may have multiple if or switch cases, so that the severity changes according to various situations. Okay, so we say that this is a high as a minimum. Then we set the confidence. We can say that we are quite certain that it's there. And then we can say that the manual review flag is not needed. So about the manual review flag, I know that I briefly mentioned this, but basically when you set the manual review flag to true, it will try to highlight in the table that is displayed that you need to verify manually if the finding is there or not. Okay. And then we can say that returns null. Okay. Okay. And then after this, we would need to add to the, maybe I spoke too soon. I need to add in the index.js in the atomic checks folder. Here, I need to specify that we will now have a new check, and that check is called not-ls reject unauthorized JavaScript check. Okay. After that, you will need to transpile with npm run build the code, and then you can test the check yourself with -l. Let's get back to the slide so that I can provide you an overview again. Okay. Wait. Okay. So this is the check that we built, and we should ask ourselves when this will fail. we can try to make an educated guess and improve
Lorenzo,
yeah.
Sorry to interrupt you. You are showing the presenter notes, so we can see the slides.
Oh, sorry. Wait. How do I do it? Let's stop the sharing. Share.
All right. Yeah. Now the.
Can you see the final result? Okay.
Yep.
So this is basically what we built. As I was saying, we are writing SAST checks, static checks. So chances are that there are some cases in which, even if we are certain that we are looking at an assignment which on the left has our string and on the right we have our 0, that doesn't mean that it will always work. For example, when there's a variable on the right hand of the expression, then we are not certain what that value will be. And we could catch that by trying to resolve the variable in that scope using the AST helper tool that I've been talking to you about. And maybe in that case, set the manual review flag and lowering the confidence. Or again, when the flag value is set to something which will be evaluated to false on runtime. And this can be because obfuscation is in place or following some transpilers or optimizations. For example, you may have seen that Webpack or Agrify AGS put not true or do some weird tricks with 1-1 and so on. And that will be obviously problematic, especially if you're trying to audit applications that are already packaged. So when you only partially have access to the source code because you're extracting the other. Again, the value can depend on some function call that returns a value when run, or maybe some decision which is taken according to the debug value. And we could go on for a while, depending on how broad we want our check to be. So that's basically it. Again, I remind you that the professional version of Electronegativity is launching soon, so keep an eye on our social media accounts to get notified when it's released. And yeah, so if anyone has any question on the check writing, feel free to use the chat here or use the Discord channel that was set up. Okay. Let me see. Okay, so no QA so far. Luca, did they miss anything?
All good. And I mean, even for professional security engagement, I mean, the first things you want to do is to run a tool like Electronegativity to get a baseline security. So I think, you know, whether you're doing it for security audit, bug hunting, or you're defending an application, I think giving a pass with the open source Electronegativity could help you figure out exactly what to check. You know, it is meant to be used by someone that really understands the concept around that. So yeah, it may not be super clear if you don't know much about Electron security, but yeah, there are many resources now online, and definitely if you will, you know, attend the full training, it will be all clear. But in any case, I mean, the online resources on Electron security at this point are pretty good.
Yeah, talking about online resources, I think we also have on GitHub a list of awesome ElectronJS hacking resources that you may want to check out. And yeah, basically that gathers all the recent talks and research or vulnerabilities that were published. So that's also very useful if you're starting or if you want to be up to date on this field.
Yeah, I just posted the link for everyone. And these are, you know, resources that we find and get notified. So if we miss something, just feel free to let us know. It's not strictly DoinSec related. It's any good thing, any good resource for Electron security would be nice to have it there, so we can all use as a community as a reference for all our works. Anything from the stream? since we have time, I guess we can open to anything, not just about the workshop. If you have any idea or anything you want to discuss around electron security, I think we could use this opportunity. I mean, we have 8 minutes to go.
Folks, feel free to pop questions in the chat box of the Q&A. If you have any for Lorenzo and Luca, feel free to raise your hand if you require it, and we can bring you onto the panel. Here's one, Luca.
All right. Yes. Are there any vulnerable Electron apps to practice on? That's a good question. I don't believe there are, open source or freely available one. As part of the training, we have developed an app that we use for hands-on exercise in the lab. It's an entire session based on a CDF-like, where you have small challenges and you need to solve those challenges. And it's meant to exercise some of the misconfiguration and vulnerabilities. We are considering at some point maybe making it open source, but at this point it's just material of the training. I'm not aware of any third party or open source one.
There's another one.
Yep. I don't know. Lorenzo, you wanna take this one, we can give two opinions. Like I think it's we might have a different opinion on this one. So Lorenzo,
I think that
go first.
One that is also the starting point for many attacks is protecting navigations. So it's crucial for your Electron app to only run trusted content whenever possible. Because even if there are some security options like the sandbox one, which may in theory allow your Electron application to also display and run JavaScript from untrusted entities, most probably when Electron applications don't do navigation protection, that's where they basically fail. So when you have access to a renderer context, you can provide your own arbitrary JavaScript. And from then on, there are many things that can go wrong from the configuration of the application. But yeah, that's basically, I think, the most common vulnerabilities that you can find, and that's the most dangerous. I don't know what Luca thinks about this.
Yeah, I mean, yeah, for sure. Like any more, I would say most of the ElectronJS exploits are usually two chains per bug. One is getting arbitrary navigation. What Lorenzo was referring to is things like new window or will navigate. And then once you have that, you need to bypass the isolation if it exists. So if the Electron is properly configured, then you shouldn't have direct access to Node.js primitives. You need to somehow bypass that, whether you use a framework bugs or a misconfiguration or vulnerability in the app. So definitely, the entry point, which could be even an XSS, but it's not necessarily an XSS. There are many other techniques on Electron that are applicable here. Is an important part of any exploit chain. I must say that with today's maturity of Electron, despite what Twitter tells you, Electron apps, on the recent version of the framework, they're pretty hard to break. Meaning, you can build secure desktop apps. It's not easy. It requires a lot of understanding of the framework. It requires new technology. It requires to do proper web security, but it is possible. And most of the engagement that we do with the major Electron apps, the vulnerability are generally either application security vulnerability, so vulnerability in the custom code, or the use of misconfiguration. So they're not bugs in the framework itself, and you can verify that by just looking at the history of vulnerability in Electron, seeing the trend it's pretty hard to find a good vulnerability in Electron right now. So yeah, I challenge everyone to go and look for more bugs in Electron frameworks. It's definitely a change since we started in 2017. It's a several weeks effort, if not month at this point.
Yeah. And to what Luca said, this is also the main reason why Electronegativity was born, right? Because when you start an audit on an Electron applications, you may want to quickly observe which window have maybe some options, some security options which are set incorrectly, or they're not preventing navigations. So that's particularly important to see the consistency of all the settings throughout the application, and then try to move and exploit them.
If there are no questions, I'm going to also do another small little rant, which is, I think, still very relevant. You know, there is a lot of talking about like this insecurity of Electron because of the old version of Chromium. And my answer to all these rants is, you know, first of all, I mean, Electron is being updated now to latest Electron pretty quickly. There are nightly builds, so if you really want to stay up to date with the Chromium, you can do it. But in particular with Chromium, like vulnerability in Chromium, they generally require like a pretty privileged type of access. I mean, you need to have JavaScript, full JavaScript execution, and things like that. So if you already do have arbitrary JavaScript execution in the context of Electron, you already bypass the step one that we just mentioned, so the arbitrary navigation. And so as a result, you just really have to bypass isolation. In other words, the last of your problem is the fact that Chrome is not updated. You know, it's probably easier to compromise the app through an Electron misconfiguration bug. So I personally don't see a lot of, to me, that's not very meaningful to kind of blame Electron insecurity based on the use of slightly older version of Chromium. But rather, I mean, the fact is that the apps and the framework version is to be, the latest version at, reasonable level, and then secure configuration. So, yeah, there's no panic when there is a new Chromium, Chrome vulnerability in the context of Electron. Those are bugs that have to be fixed, but they do not require all hands on deck type of emergency. If you're concerned about that, I think there are major problems in the app beside the use of old Chrome and lib Chrome content.